Good day and welcome to another tutorial on this YouTube channel. I remain your host Abasolaya, and today we'll be treating matrices and how to use the knowledge of matrix to solve systems of linear equations and how they apply to what we want to do on the long run, which is using them to actually indicate what they are used for in machine learning and deep learning generally. So join me as we go into today's tutorial. So basically we are doing matrices to lay a foundation for most of the things we'll be doing. And mind you, matrix is like something under, what's it called? It's something under linear algebra. So basically, let me just define some basic terms before we move on. So machine learning is about designing algorithms that automatically extract valuable information from data. So basically, when we are doing machine learning, what we are basically doing is we are writing an algorithm that extracts valuable information from data to make some predictions in the future on some other data. So the basic things we need, the basic terms we need to master when it comes to machine learning are data, learning, and model. So data is what we need. So data is like the oil. Then learning is what your algorithm actually does. Then the model is the algorithm you write, like the model you create to do all these things that you are doing. So a model is typically used to describe a process for generating data similar to data set at hand. So you can have a regression algorithm, you can have a density estimator, you can have a dimensionality reduction, you can have a classification algorithm. So all these things are models to generate data from data. That is, you have data at hand, you learn from that data. So when you see a new data point, you generate another data. That is, you are making some predictions on the new data point that you are having. So that's basically that. So moving on to linear algebra now. So linear algebra is a study of vector and certain rules to manipulate vectors. So basically linear algebra is what we are doing today. I know I mentioned matrices, so linear algebra. So linear algebra is the major thing we are doing today. And the reason why I mentioned matrix is most of the things we'll be doing actually will be focused on matrix. But matrix is like a subtopic under linear algebra. And basically, matrix are built from vectors. And you can see linear algebra is study of vectors. So since matrix are built from vectors, so by inference, linear algebra is linear algebra is a study of vectors. And vectors matrices are built from vectors. So we can say linear algebra is a study of matrices too. So having said that, the matrix the vectors you are used to by now are the vectors that you see that looks like this. These are the vectors where you were taught in probably your high school or your secondary school or like that. So basically these vectors that you are seeing here are what we call geometric vectors. Geometric vectors in that they are directional vectors. It's just a type of vector. It's an example of vector. We have a lot of them. We have geometric vector. We have what we call the polynomial vector. We have what we call the audio signals and the likes like that. So moving on from there, let's quickly express vectors now. Vectors are special objects that can be added together, multiplied by scalars to produce another object of the same kind. I don't know if you get me. Vectors are special objects that can be added together, multiplied by scalars to produce another object of the same kind. So if you can add two things together, and at the same time you can multiply it by a scalar object. What I mean by a scalar object is any element of the real number system. Any element of the real number system is what we call a scalar. So if you can multiply it by a scalar to get something else, to get probably a bigger vector or a smaller vector that's still of the same kind of vector, or if you can add it together with another vector to produce a new vector, that's what we call vector basically. That's what we call, I was referring to them as vectors already. I'm supposed to refer to them as objects. So if you can add two objects together to form a new object, and at the same time you can multiply any of those objects by a scalar to produce another object, maybe larger or smaller, of the same vector type. Of the same object type. That's what we call a vector basically. So moving on from there, we have examples of vector. So the ones you are seeing on my screen now are what we call geometric vector. And the reason why we can call them vectors is very basic. The reason why we can call them vector is because we can add them together. So we can add A plus b together. So geometric vectors are just directional vectors. We are already familiar with them in our high schools. So this is a geometric vector. Now you can add a and b together to form c. So you can add that's basically that. You can add x. Someone's already saying, why must you write x in mathematics? Don't mind me. That's what we use most of the time. So I'm used to it. So that's why I'm using x again here. So that's an example of a geometric vector. Then we have polynomial vector. We call them polynomials. Polynomials are also vector. I just call them polynomial vector because polynomial is a vector. So like more like tautology. So basically we can add two polynomials together. So we can have, let's say, look at this plot here. Don't mind me that I'm crossing into another vector. So this x, this y. We can have each of them as geometric. Then having x plus y. So that's an example of a geometric vector when we're adding them together. I'm just giving you a pictorial view. So polynomial now, all of us know polynomials now. All those squiggly lines that looks like this. Actually, they are a bit abstract to some extent. But don't look at them as being abstract because we are still going to use them in our machine learning algorithms. We are still going to use them, but we are not going to call them polynomial vectors at that time. We are going to call them real tuple of real numbers. That's what we'll call them. But just look at this now. So this is a polynomial. And the reason why we said it's a vector is because we can add two of them together to form a new vector, and you can multiply it by a scalar. Because all these points that you are seeing here are basically points on the real, are basically points that you can multiply numbers by. That's -4, -2, that's -2, we have 0, then 2, then we have 4, like that. So these are polynomials, for example. So they can be abstract to some extent, but don't see them as abstract yet because we are still going to do some pretty basic things with them. So you can multiply any of them. That is, let's say this y now. You can multiply lambda times y to form a new vector lambda y, and you can add x and y together, x plus y, to form a new vector, maybe z, something like that. So that's an example of polynomial. Then we have what we call audio signals. So audio signals are basically things that you can represent with a series of numbers. For example, what you hear from your MP is an example of audio signal. You can actually add audio signals together. That's where we have music, we have our beats, and we have our lyrics. So when we bring them together, that's why we can have danceable songs. That's why some people say, I can dance to this song, but I can't dance to this song. Whereas the two songs are produced from the same beats. And it's because probably the lyrics is not going in tandem with them. So that's that on that. So basically, we can add audio signals together. You can bring two signals together, and you can multiply a audio signal with a real number. That's where you have volume. When you are, I'm just using your sound, like the sound system you use in your house, as an example of an audio signal. We have a lot of audio signals. In fact, there are some that we cannot hear with our human ear. So that's an audio signal for you. So you can add them together. You can multiply them by real numbers to produce higher volumes or lower volumes when it comes to your sound system and the likes like that. Then we have another type of vector that we call tuples of n real numbers, and that will be the focus of our course of our learning in this aspect of things. So why do I call them tuple? How do we call them tuple of n real numbers? See an example: a equals 2, 3, 4. This is an element of n real numbers. This one is 3. So normally what we say is they are element of n real numbers. That's the power of n. So that n is a natural number. What we mean by natural number is count numbers. So we have 1, 2, 3, 4, 5, 6, like that. Don't mind Python that starts counting from 0. Our natural number starts from 1. So that's a vector of n numbers, and that will be the focus of our lectures. So we can have a plus b to give us c. We can have lambda times a to give us maybe lambda e. So let me just give you an example of that. So 2, 3, 4 plus 1, 2, 3. So this will basically give us 3, 5, 7. So this is what this will give us. And if we multiply them by let's say 2, which is an element of the real numbers, so multiply by 2, that's 2, 3, 4. We can have 4, 6, 8. So that's that on that. Moving on to the next thing. So basically, we can now use the knowledge we now have to solve a system of linear equations. For example, if you remember simultaneous equation were in secondary school, that's a system of linear equations actually. So you can bring them down. Actually, I will solve them as system of normal equations, the way we did simultaneous equation in secondary school. Then on the long run, we'll bring them down to matrices. Then we start solving them as matrices. So let's start system of linear equations. So systems of linear equations. So that's that on systems of linear equations. So let me just give you an example of a system of linear equation. Let's say x1 plus x2 plus x3 is equal to 3. Then we have x1 minus x2 plus 2x3 is equal to 2. Then we have 2x1 plus 3x3 is equal to 1. So this equation now, it looks like the normal simultaneous equation we did in secondary school, right? So let's add equation 1. Let's call this equation 1, equation 2, equation 3. Let's add equation 1 and equation 2 together and see what it will give us. So we have equation 1, that's x1 plus x1 will give us, let me just write it out, x1 plus x2 plus x3 is equal to 3. Then we have x1 minus x2 plus 2x3 is equal to 2. So adding these two together will give us 2x1. x2 minus x1 will automatically give us 0. Then plus 3x3, which is equal to 5. And comparing this to our third equation, that was our third equation, which is 2x1 plus 3x3 is equal to 1. You can see these two things are contradicting. How will 2x1 plus 3x3 give us 5 and at the same time give us 1? It's not possible. So this type of equation, we say they don't have a mathematical solution. There is no solution to this equation, for example. Then we can have another one. That can have, don't let me put the cat before the horse here. So plus x2 plus x3 is equal to 3. Then x1 plus, x1 minus x2 plus 2x3. Don't mind me, the equations look like one another, but they are not the same actually. Then 2x1 plus 3x3 is equal to 5. Actually, if you check this equation well, if you add equation 1 plus equation 2, it will give you equation 3. That's x1 plus x1 will give you 2x1. x2 minus x2 will give you 0x2. Then x3 plus 2x3 will give you 3x3. Then 3 plus 2 will give us 5. That's where the difference happened. So moving on from there, we can simply do what? Make x1 subject to formula or something. So we can have x1, that's 2x1, subtracting 3x from both sides of equation 3. 3x3. So we have 5 minus 3x3. So 5 minus 3x3. So 5 minus 3x3, that's 2x1 equals 5 minus 3x3. So x1 is equal to, dividing both sides by 2, that's 5 minus 3x3 over 2. All of them over 2. So having that now, we can now bring this into equation 1 or 2. to get our x2, for example. So our x2 will now be, that's 5 minus 3x3. Sorry. Used to 5 minus 3x3 over 2 minus x2 plus 2x3 is equal to 2. So next page now we have 5 minus 3x3 multiply both sides by 2 actually, so you can eliminate this over thing that we have here. So let me just erase everything. So 5 minus 3x3 then minus 2x2, we are multiplying both sides by 2, plus 4x3 is equal to 2. Equal to 4. So collecting like terms now, that's basically where you now you subtract 5 from both sides, then you collect like terms here. So 4x3 minus 3x3. So adding these two together will give us x3 minus 2x2, which is equal to minus 1. So that's equal to minus 1. Yeah, that's equal to minus 1. Then what else do we have? Then we subtract 2x2 from both sides. So that's x3 equal to minus 1 plus 2x2. Oh, sorry. I made a mistake somewhere. So let's quickly erase this aspect of things. Let's quickly erase this. I'm doing it in terms of x3. So I'm not supposed to be looking for x3. I'm supposed to be looking for x2. So subtracting this from each other, we have that's what's going on? x3 minus, that's x3 minus, what's it called now? That's x3 minus 2x2, which is equal to minus 1. So now, subtracting x3 from both sides, we have minus 2x2 is equal to minus 1 minus x3. Then dividing both sides by minus 2, we have x2, which is now equal to minus 1 minus x3 over minus 2. Yeah, minus 2. Sorry, I need to erase that. So moving on to the next page now. So our x2 is basically equal to 1 plus x3 over 2. So now our x1, x2, x3 is now equal to 5 minus 3x3 over 2, 1 plus x3 over 2, x3. Then we can easily replace x3 by a, and we have 5 minus 3a over 2, 1 plus a over 2, then e, which is our x1, x2, and x3. So that's how we solve system of linear equations. And that's what we basically call simultaneous equation in secondary school. So I just illustrated that we can have system of equation that will not have solutions at all with this one. This one does not have this one does not have solutions, any solution, whereas the final one we did had multiple solutions because our x3 can take any value on the real number system, and we replaced it with a now. So let me just write it out for us on the next page. So we have 5 minus 3a over 2, 1 minus a over 2, a. So a can take any value. So a is an element of the real line. So it can take any value on the real line. So that's why we say it has infinitely many possible solutions. So moving on from there now, then we can have an equation that can have a unique value. What do I mean by a unique value? Look at this equation. 4x1 plus 4x2 equals 5. Then 2x1 minus 4x2 equals 1. So if we add these two equations together, basically this is equation 1, this is equation 2. So if we add these two equations together, we have 6x1, which is equal to 6. So x1 is equal to 1. Then on to the next page now. Then putting x1 equals 1 into equation 1, for example, that's 4x1 plus 4x2 equals 5. So putting x1 equals 1 into equation 1 now, we now have that's 4 plus 4x2 equals 5. Subtracting 4 from both sides, we have 4x2 equals to 5 minus 4, which will give us 4x2 is equal to 1. So we have x2 is equal to 1 over 4. So that's our final answer. So x1 is equal to 1, x2 is equal to 1 over 4. So that's how to solve. So our system of linear equations can have one of three solutions. It can have no solutions at all. It can have multiple solutions, that is infinitely many solutions. Then it can have a unique solution. So having said that, we can then move on to representing system of linear equations as matrices. So for example, let me just give you this example. These are 4x1 plus 4x2 equals 5 and 2x1 minus 4x2 equals 1. So we can write this one as a matrix, for example, like this. We can have 4, 4. Then we have 2, minus 4. Then we have a vector of x1, x2, which is equal to 5, 1 in another vector. So that's how we represent our equations in a vector, in a matrix form. So we represented these two equations in this form, for example. And most of the time we don't put the comma. So don't be confused. If you don't see any comma, you just see the spacing between them. That's a system of linear equation. This tutorial is getting long, so I will stop here. And in our next tutorial, we'll dive straight into treating matrices. Thank you for joining today's class. See you in the next class.